We've talked about inadmissibility of estimators, primarily motivated from a frequentist perspective. But it turns out, so in this video we're going to look at a Bayesian approach to choosing a decision rule. And it turns out that in fact Bayesian approach is optimal in a certain sense, even with respect to the frequentist concept of admissibility. So I'm drawing now, remember our diagram here, we had our loss, and you could go one of two directions. You could either take the expectation with respect to the parameter given the data, and that gives you the Bayesian expected loss, or you could take the expectation with respect to the data given the parameter, and that would give you the frequentist risk. And when you took the expectation of either of those again, you got back to the same place, and that was just the Bayes risk. And so that was on the right we had, in red we had risk world, and on the right and on the left we had Bayesian world. So let me just remind you what these definitions were for in Bayes world. Now we're going to play around in Bayes world. The Bayesian expected loss was this rho of pi, and let me use delta of d for a decision rule. Delta of d, that action or that choice, that estimate, was the expected value of the loss at the point theta, at theta, the true theta, and our estimator given the data. That was the Bayesian expected loss, and the Bayes risk, a function of pi and delta, was just the expected value of the loss, the whole thing, not conditioned on anything. And let's play around with this a little bit here. This is we can always write this. Let's go ahead and we can rewrite this if we use the law of conditional expectations. This is the expected value of the conditional expectation of the loss given, did I get enough parentheses there? Let's see. Boom, boom, yep. Given the data. That's just the law of conditional expectations. You can prove that just by writing out the definitions of the conditional expectation. And what is this? What is this thing in the middle here? This is just the Bayesian expected risk. That was just this top thing, rho. So this is the expected value of rho of pi with delta of d. So it's just the expected value of our Bayesian expected loss. So now remember, when we were talking about the Bayesian approach, we talked about two cases. You could either, in the first case, which was corresponding to this sort of thing, if you knew the data that you were going to be sort of evaluated on or tested on, then you would just choose the action, choose the delta of d, that would minimize this expected loss, this posterior expected loss. It's the posterior distribution given the data. And the other case was if we didn't know what d we were going to have to choose an action for, then we wanted to minimize the Bayes risk. That was what we talked about. Choose a delta to minimize the Bayes risk. And here it turns out this suggests that in order to minimize the Bayes risk, we should just choose the action delta of d to minimize the Bayesian expected loss, this first thing, for each d. So this suggests, so let's actually make a definition. This will lead us to the definition. And now, so for the rest of this video, I'm not really an expert in this area, so the rest of this should all be sort of taken with a grain of salt. And there's some sort of conflicting definitions that I've found. There's not uniform agreement on the definitions of these things. So since I'm not an expert, I don't want to make this seem authoritative. So with that disclaimer, let me just say the rest of this is an informally. informal discussion. So with that disclaimer, a generalized Bayes rule. I wanted to go through this though because it's really interesting and at least to give you the general idea of what's going on. A generalized Bayes rule is a decision rule, delta, minimizing the conditional, or rather the Bayesian expected loss, this thing, for each d. For any possible data, you choose your delta of d to minimize this. And that's just exactly what we were talking about here. And it's not too hard to see that that's going to minimize your Bayes risk. So if that's a generalized Bayes rule, what is a Bayes rule? Well, a Bayes rule it's also a decision rule, and it minimizes just the Bayes risk. So it's a decision rule delta that minimizes this. And that was just what we talked about. If you didn't know what data you were going to be asked for ahead of time, or asked about ahead of time, then you minimize this. And that's what's called a Bayes rule. So in some sense, this sort of corresponds to case 1, and this sort of corresponds to case 2. But it turns out that they're essentially, if we solve case 1 for every possible value of the data, then we also solve case 2. And so we have the following. Let me call this a GBR. Just for shorthand here. A generalized Bayes rule. Any generalized Bayes rule is a Bayes rule. That's pretty clear to see just from the definitions. But not every Bayes rule is a generalized Bayes rule. And the reason for that is, well, one of the reasons is that your prior might put 0 probability on some regions, and on those regions a Bayes rule is essentially arbitrary. So let me make a couple of remarks about this. So here's a first remark, which is that if the Bayes risk is infinite for every decision rule, then anything, right? You're trying to minimize that when you choose a Bayes rule. But if that's just infinite, then anything is a Bayes rule. But, and this can happen, particularly this can happen when you have an improper prior. But a GBR, a generalized Bayes rule, still makes sense. So this still makes sense. This is a sensible thing to do because, there might be some data for which, this is averaging over everything, over all the possible data. But there might be some data for which, there's some finite value here for the expected Bayes loss, the Bayesian expected loss, and you certainly should try to minimize that whenever you can. Because if you were to happen to get such a data, then you would want to do something sensible. So this is a generalized Bayes rule is in some sense preferable. It's sensible even when the risk is not, when the risk is infinity, the Bayes risk. And another comment here is that on sets of pi measure 0, if your prior puts 0 measure on certain possibilities of theta of the parameter, then a Bayes rule is arbitrary because you're minimizing this expectation. The Bayes risk is an expectation over over theta with respect to your prior pi, and if you're putting zero probability under pi on some thetas, then your Bayes rule is just going to be arbitrary on those sets. Is arbitrary on those sets. The Bayes rule is arbitrary, but GBR, generalized Bayes rule, still makes sense. Is still, I'll say, is still sensible. Does the right thing. And now there's a beautiful, so this is all informally again. I'll insert my disclaimer again. I'm not an expert in this area with respect to generalized Bayes rules and all of this, but this is the general idea, and I wanted you to at least to see the general idea. And here is the beautiful result. All of this sort of wrapping this all up together into with the concept of admissibility. So there's the complete class theorems, and I won't give a formal statement of this, but what it says roughly is that under mild conditions, every generalized Bayes rule, this is for a proper prior pi, is admissible. So this is very reassuring. This is saying that as long as we have a proper prior and we choose a generalized Bayes rule, then we're guaranteed for it to be admissible under certain sort of mild conditions here. And so that's reassuring. And furthermore, every admissible decision rule is a generalized Bayes rule for some prior pi. And here this pi could possibly be improper. So this is a very nice sort of justification or motivation for why you might want to take a Bayesian approach, because even with respect to the frequentist notion of admissibility, by taking a Bayesian approach, you're essentially guaranteed admissibility. And furthermore, you don't need to look anywhere else. There's nothing sort of, so part B is saying there's nothing sort of outside of the Bayesian world that could possibly be better. That's what part B is saying. Part B is saying there's no decision rule, under these sort of conditions. There's no decision rule that you could obtain by not taking a Bayesian approach that would dominate the Bayesian, that would dominate every Bayesian approach. So this is nice. Well, I should say it's reassuring at least. And this doesn't give a complete justification for why Bayes is always sort of better in some sense, because remember that admissibility is sort of just the weakest sort of, it's just the bare minimum of what you would want an estimator to do. Remember, because for example, we had the example of the silly estimator, and that was admissible. So admissibility, while it's certainly something that you would want to have, it does not guarantee that your estimator is not silly. So it does not guarantee that it's necessarily a good estimator. All right, so this was generalized Bayes rules and Bayesian decision theory, and I hope that was informative to you.